Welcome everyone. Today, we'll discuss high-temperature creep and creep fatigue interaction, two critical phenomena affecting material behavior under combined stresses. These concepts are essential for ensuring safety and reliability in high-temperature systems. Overview of high-temperature creep and creep fatigue. High-temperature creep and creep fatigue interaction are critical considerations in the design and maintenance of components operating under elevated temperatures, such as steam lines and boiler headers. These phenomena occur when materials are subjected to prolonged stress at high temperatures, leading to time-dependent deformation and eventual failure. Understanding these mechanisms is essential for ensuring structural integrity and safety in power plants, petrochemical facilities, and other high-temperature environments. This presentation will explore the fundamentals of creep, its impact on fracture mechanics, and how cyclic loading combined with creep accelerates damage. We will also review assessment methodologies outlined in API 579 Part 9 and BS 7910, providing practical examples to illustrate real-world applications. By the end, you will gain insights into failure modes, preventive strategies, and engineering best practices for managing these risks. Effect of high temperature on fracture behavior. At elevated temperatures, materials exhibit significant changes in mechanical properties, including reduced yield strength, increased ductility, and altered fracture toughness. These changes influence crack initiation and propagation, as stress redistribution occurs around crack tips due to creep deformation. Fracture mechanics principles must account for time-dependent behavior, where stress intensity factors evolve as cracks grow under sustained load. High-temperature conditions also promote oxidation and microstructural degradation, further weakening the material. In components like steam lines and headers, these effects can lead to catastrophic failures if not properly assessed. Standards such as API 579 Part 9 and BS 7910 provide guidelines for evaluating fracture behavior under creep conditions, emphasizing the need for accurate material data and stress analysis to predict remaining life and prevent unexpected breakdowns. Understanding creep mechanisms and crack growth. Creep is a time-dependent deformation process occurring under constant stress at high temperatures. It progresses through three stages: primary, decelerating strain rate; secondary, steady-state strain rate; and tertiary, accelerating strain leading to failure. Mechanisms include dislocation creep, where dislocations move through the lattice; diffusion creep, involving atomic migration; and grain boundary sliding, which weakens structural cohesion. These mechanisms collectively contribute to material elongation and stress redistribution, influencing crack growth rates. In fracture mechanics, creep crack growth is modeled using parameters like C integral, which accounts for time-dependent plasticity. Understanding these mechanisms is vital for predicting component life and implementing inspection intervals. Failure to address creep effects can result in sudden rupture, especially in high-pressure steam systems where thermal stresses are significant. Interaction between creep and cyclic loading. Creep fatigue interaction occurs when components experience both sustained high-temperature stress and cyclic loading, such as during startup and shutdown operations. This combination accelerates damage accumulation because creep deformation weakens the material, making it more susceptible to fatigue crack initiation. Failure modes include intergranular cracking due to creep and transgranular cracking from fatigue, often observed in boiler headers and turbine components. Assessment requires considering both time-dependent creep damage and cycle-dependent fatigue damage, typically using damage summation approaches like the linear damage rule. API 579 Part 9 and BS 7910 outline procedures for evaluating these interactions, emphasizing accurate load histories and material properties. Understanding these failure modes helps engineers design components with adequate margins and implement maintenance strategies to mitigate risk. Assessment methodology, API 579 Part 9 and BS 7910 guidelines. API 579 Part 9 and BS 7910 provide comprehensive frameworks for assessing high-temperature creep and creep fatigue damage. These standards recommend evaluating material properties, operating conditions, and stress distributions to estimate remaining life. Key steps include determining creep rupture data, calculating stress intensity factors under creep conditions, and applying damage accumulation models. For creep-fatigue interaction, the guidelines suggest using combined damage approaches, where creep and fatigue contributions are summed to assess total damage. Advanced methods like finite element analysis are often employed to simulate stress and temperature gradients accurately. These assessments enable engineers to make informed decisions on component repair, replacement, or continued operation, ensuring safety and compliance with industry standards. Practical examples: creep crack growth in high-temperature steam line, creep fatigue failure in superheater header. A common example of creep damage is observed in high-temperature steam lines operating at pressures exceeding 100 bar and temperatures above 500 degrees Celsius. Over time, thermal stresses and sustained loads cause creep deformation, leading to crack initiation at welds or bends. Using API 579 Part 9 methodology, engineers calculate the C parameter to predict crack growth rates under creep conditions. Inspection data, such as ultrasonic testing, helps validate these predictions and determine remaining life. Preventive measures include material upgrades, stress relief heat treatments, and periodic inspections. This case highlights the importance of proactive assessment to avoid catastrophic failures that could result in costly downtime and safety hazards. Superheater headers and heat recovery boilers often experience severe creep fatigue interaction due to frequent thermal cycling and sustained high-temperature exposure. Cracks typically initiate at ligaments between tube holes, where stress concentration is high. Assessment involves calculating both creep damage during steady operation and fatigue damage during startup/shutdown cycles. BS 7910 provides guidance on applying fracture mechanics principles to evaluate crack growth under combined loading. Mitigation strategies include redesigning ligaments, improving weld quality, and implementing controlled startup procedures. This example underscores the need for integrated analysis and maintenance planning to ensure long-term reliability of critical components. Design, preventive measures, and best practices. Preventing creep and creep fatigue failures requires a combination of robust design, material selection, and proactive maintenance. Design strategies include using alloys with high creep resistance, optimizing component geometry to minimize stress concentrations, and applying protective coatings to reduce oxidation. Maintenance practices involve regular inspections using advanced non-destructive techniques, monitoring operating conditions, and implementing life extension programs based on accurate damage assessments. Standards like API 579 and BS 7910 serve as essential tools for engineers to evaluate risks and plan interventions. By adopting these best practices, industries can enhance safety, reduce downtime, and achieve cost-effective operation of high-temperature systems. Let's see summary, key takeaways and standard references. High-temperature creep and creep fatigue interaction pose significant challenges in the operation of critical components. Understanding the underlying mechanisms, failure modes, and assessment methodologies is essential for ensuring structural integrity. API 579 Part 9 and BS 7910 provide robust frameworks for evaluating these phenomena, guiding engineers in making informed decisions. Practical examples demonstrate the importance of accurate analysis and preventive strategies. By integrating these principles into design and maintenance practices, industries can mitigate risks and achieve reliable, safe operation of high-temperature systems.